Good afternoon, I'm Paolo Geremia and I'm the General Manager of ENGYS in Italy. Today I'm going to talk about the new features and enhancements in HELYX version 3.5. Let's start off with a bit of background before we move into the main topic of this presentation. So let me just mention a few words about our company, ENGYS. We are global providers of CFD products and services. The company was founded in the UK in 2009, and our main focus has always been on open source software for enterprise. And there is an historical reason for that. In fact, we have been involved in foam and open foam development since 1999. This means that we gained a know-how in this open foam technology that we decided to create our own open source software products. We currently have more than 200 active customers around the world, and this includes both products, software products, and services. Services are basically engineering consultancy services and custom development services. We serve our clients through 8 offices worldwide, and this includes 4 locations around Europe and 2 in the Americas. And where we don't have a local presence, we rely on a well-established network of resellers. In terms of how our vision reflects on the quality of our enterprise CFD products, we try to combine the well-known benefits of the commercial CFD software with the inherent advantages of the open source CFD technology. This means that we offer an easy-to-use graphical user interface, a GUI, for all of our software products. We provide also best-in-class technical support to our clients and extensive written documentation, as you might expect from a commercial software. In terms of open source CFD technology benefits instead, we offer full capacity of code customization, so the software is fully transparent, is not a black box anymore. You can check inside the code and see what's implemented. And free scalability, which means no extra license costs due to parallel or HPC runs. And this provides a set of very compelling and cost-effective solutions. Our 2 main CFD enterprise products are HELYX and Elements. HELYX is an open source CFD software for enterprise, whereas Elements is an advanced CFD software for automotive design. In addition, we also have a series of add-ons which are advanced modules for specific engineering applications. So we have HELYX Adjoint, which is based on a continuous adjoint formulations, which allows you to solve both topology and shape optimization problems. HELYX Coupled, which consists of a series of block coupled solvers for both incompressible and compressible flows. HELYX Marine, which includes a set of tools for ship hydrodynamics. And finally, HELYX Hydro, which is based on an advanced volume of fluid solver for free surface flows. Let's now move into the main topic of this presentation. HELYX version 3.5 is the standard release of the HELYX system, and it includes a series of new features and enhancements in all the main software components, including mesh, setup, solver, and view. And today I'm going to do a walkthrough of the main features and functionalities available in each single component. Let's start with mesh. So for more than 2 years, we have been putting a lot of efforts in improving our mesh generator, in particular for the creation of low Reynolds grids. And in this context, the snapping stage, which represents one of the critical parts of the mesh generation process, is really key to determine the accuracy of the resulting mesh. So for example, when you have to mesh acute and reflex angles, such as tire contact patches and sharp trailing edges, like the one I'm showing here in this slide, it's very important that these are accurately snapped to allow successful layer growth. What we did was to define a threshold angled, a mean and max value, to extract a plane-to-plane line intersection to snap the edges into these. And this is available, these controls are available from within the GUI and can allow the user to deal with these kind of problems. In addition to this, we also refactor the existing snapping algorithm to deal with grown-up patches, not necessarily planar ones. And finally, we improved on the enhanced performance and CPU time of the snapping stage. In addition to snapping, we also improved on the near wall layer controls. And in this regard, we added an option to prescribe the maximum layer thickness for the dual and extrude mesh algorithms. So if you leave the maximum layer thickness undefined, this is what you end up with. You can see here on the top image, you will have a thick boundary layer, like in this case, whereas if you specify the maximum layer thickness to a specific value, this is what you get. So there is more control now available in 3.5 with respect to the previous version. In addition, we added a new mechanism to split cells based on a warpage criteria, which is a measure of how much a phase point is out of a phase plane that it should lie on. And this can be controlled via an absolute or a relative value to the near wall layer height. And finally, we improved on the overall performance of a single step layer projection. We also improved on the mesh optimization phase and quality measure. So for the optimization part, we added faster mesh optimization settings for both the snapping and the layer addition phase. So in previous version, the user basically didn't have any control on the optimization stage. So this means that all the quality checks, including phase area, phase warpage, pyramid volumes, and tetrahedral volumes, were performed during both the snapping and the layer phase. But this very often resulted in a very high turnaround and computational times. So it can be important to have the full optimization only during the snapping stage, and then use relaxed settings. So for example here, only for the layers stage, to reduce the costly final optimization stage. And you can see here there is a selective check here that the user can have in the GUI, in the graphical user interface. In addition, we added a quality metrics panel to remove bad cells or phases. So you can see here that you define, you can tick on specific criteria to remove cells not meeting this and satisfying this criteria. you can also create a specific patch for post-processing and visualization purpose in case you want to visually inspect. Another important feature that we added to the mesh component is the visual mesh leakage detection you can have inside the GUI. So there is a new tool in the GUI to detect any mesh leak. So you can see here that we have a component which is not watertight, and what happens is that the mesh spills out of the internal fluid volume, and to visualize this you have the so-called leak path, which can be clearly seen in the 3D display. To achieve this, you need to define a point which is outside the flow domain, which can be reachable from the material point which falls inside the fluid domain instead. One important enhancement I would like to mention is the new binary surface file format, BTS, for geometry files. In the first graph shown here, you can assess the efficiency of the new format versus the old one in terms of disk space. So on the x-axis, we have the number of faces of the geometry file, whereas on the y-axis, we can see the file size in megabytes. In terms of I/O, you can see that for both the read and write time, the new BTS format outperforms the old one and also scales with the number of cells. In the mesh GUI component, we also added a tool to export surface mesh patches to triangulated format, either STL, binary or ASCII, or ENGYS, binary surface format. And this is shown here as an example on a surface mesh patch. Now let's have a look at the other improvements available in the mesh module. So first, there is a new functionality which lets you create cell zones via geometry file and multiple outside points. What does it mean? So you have a geometry file here, like the one shown in gray here, and then you want to define two cell zones outside the geometry, and this is done via the definition of 2 points outside this geometry. You can do it from this panel in the GUI, inside the cell zone panel, and this will automatically create these two cell zones in one go, the one shown in red here. Then we have this increment, decrement number of layers at patch interface, which means that you can choose to either increment from lower layer count patch or decrement from the higher layer count patch. And this is only applicable when you use the extrude mesh method. Finally, we have a tool inside the mesh component to filter out small edges. So when you have, for example, noisy triangulated surfaces, this can generate spurious feature edges. And this can then be selected for feature refinements, and this of course will result in bad quality meshes. So this capability, which is based on the definition of a minimum feature length by the user, allows you to get rid of these small feature edges. Let's now talk about setup. The first feature I would like to talk about is the mixing plane boundary. In version 3.5, we have a new discrete mixing plane boundary condition for turbomachinery applications. This works based on a generalized MRF approach to construct a full 360 degrees model based on stator impeller sector model. So it basically applies a discrete averaging type in the circumferential direction to calculate velocity and the other fields. This is applicable if the ratio between the number of stator and impeller blades is a non-integer value, and worse only for steady state flows. As you can see here, this is fully supported by the GUI. Similar to discrete mixing plane, we also have the periodic cyclic AMI, which is a boundary condition for stator impeller sector models. And it's only applicable if the ratio between number of stator and impeller blade is an integer number, contrary to what happens in the discrete mixing plane here. This can be applied to both static and dynamic meshes here. So you can see here an example of an impeller rotating and connected via this periodic cyclic AMI to a diffuser here, which is also connected in turn to the volute via another periodic cyclic AMI. This is fully supported by the GUI. And as I said, it runs both in steady state and transient mode. In terms of boundary condition, we have a new time varying map data temperature boundary condition, similar to what we already have for velocity and pressure. And also we have a new boundary condition for total pressure. More specifically, we have a new static head option to define a different criteria to calculate the static head. So instead of assuming the constant density, you can have the integral of the density across the surface. So instead of a linear, you can have a parabolic profile. In terms of wall function, we have a new adaptive rough wall function based on the NOP formulation. This means that we have a roughness independent of the y plus values. So if you look at the example shown here, where you find a smooth curve in gray, and the standard formulation of the roughness wall function that we previously have in HELYX, you can see that for a low Reynolds grid, there is no difference with respect to a smooth wall, whereas for a high Reynolds mesh, in this dashed red curve, you can see that there is the correct velocity shift. Whereas if you want to use the new NOP consistent rough wall function, you can see that the velocity shift is consistent for both the low Reynolds mesh, the continuous line, and the high Reynolds grid, the dashed one. Looking at monitoring functions, we have the few additions for the turbo performance. So now the turbo performance function calculates all the quantities of interest for the full 360 model in case you use a sector model using either the cyclic periodic AMI or the discrete mixing plane, the boundary condition I showed earlier. And it also outputs additional fields such as flow rate, density, and others. There's a new function to calculate statistical quantities on any function that you can have inside the HELYX model, and this includes moving average, standard deviation, coefficient of variation, etc. In terms of data export, there is a new functionality for the surfaces export. So basically, we added an option to compute an internal feed at a prescribed offset distance from a mesh patch and save it to VTK format that you can open in third-party post-processing tools. And this basically provides a very useful feature to measure flow at a certain distance from the specific surface. In the solver module, we have a new custom field calculator, which allows you to calculate custom and user-defined fields at runtime using a specific function object or as a post-processing task. What you can do is the definition of your own formulas. You can enter here using this calculator panel, and once you're done, you can save the custom fields in the so-called formula library that you can later use. In terms of monitoring, we added a new function to monitor the percentage of volume model using either runs or LES. And this is, of course, applicable when you use a DES-based model, such as DS or delay detach dissimulation or IDDDS and so on. And you can see here, this graph, you can have a percentage as a function of time of the LES and runs volume coverage inside the domain. But in addition to that, you also have an additional LES/runs switching field to visualize the LES and runs regions in the mesh respectively. So in the blue area here, you can see where the runs is applied. In the red area is where you have the LES region. Now, moving to the View tab, we have a new modifier which applies transformation to an existing object. So you can have a mirror, translation, rotation, scale, or a linear or cylindrical array. Like in this case, we have a cylindrical array to move from a single sector model to a full 360 degrees model. And the important thing to keep in mind here is that you can combine different transformations, one on top of the other. And this is also supported by runtime visualization if you want to create in batch mode post-processing images. A useful feature for post-processing purposes is the point widget. This allows you to visually inspect field values on selected points in the screen. So this includes, of course, mesh, volume, cells, or surface patches, or even mesh objects, like in this case where we have a slice and we want to measure the velocity on a specific location down here. And finally, you are also able to visualize the location and the value and copy this value accordingly. There is also a list of minor features which were added, including case reload optimization by selective loading of modified components only in the GUI, additional options for the atmospheric boundary layer using the synthetic turbulence generator to use an implementation of a turbulent kinetic energy consistent with the AIJ formulation, CAIP decomposition based on an efficient multi-level graph partitioning algorithm as an alternative to the existing Scotch decomposition method. Then we have the case preview, which allows you to open a case and visualize for the specific case a few statistics about the case structure, whether it's serial, parallel, number of processors, multi-region, number of cells, and also a picture shown here. And then finally, other minor features and a number of bug fixes. To conclude my presentation, today we introduce the new features and enhancements available in HELYX v3.5, which was released in April 2022. And this is a standard release with several improvements made available for the various software components to provide increased performance and enhanced usability. In terms of release roadmap, the next major version is v4.0, which is due for release between winter 2022 and spring 2023. Between now and v4, we will launch a new bug fixes release program, which will provide our users with patches delivered on a regular basis, including, of course, our on-demand services at Cirrus and Penguin Computing. These updates will not be advertised, so please check our portal to make sure that you always use the latest version of HELYX. Finally, looking at the next development cycles, our focus will be, among other things, on multi-physics, and in particular on a new unified solver framework as solution platform. Finally, you are all cordially invited to our user group meeting in Detroit in the US later this year, and you can find here the link for the registration. Thank you very much for your attention.